Hi, everyone. I'm Zhuolin, and today I'm going to talk about our paper towards a general video-based keystroke inference attack. And this work is jointly done with my colleague, Yuxin, Zain, Hadleigh, and my advisors, Ben and Heather. So I'm sure we all had this experience. We found ourselves no longer just work in the office and our home, we even work on the go. Lounges, cafes, airports. And in fact, on my trip from Chicago to here, I was working and typing in the airport. I mean, deadlines, right? We are used to that. But when we work, we type sensitive text, work emails, research proposals, private documents. But as a person who works in security, I want to ask, is it safe to do so? Should we type in public spaces? Could there be an attacker? They're in the same public space with us. They're observing our typing. And by just doing that, they can guess our keystrokes. And eventually, our entire sensitive text. Now, this is very concerning. But the real question here is this a practical attack in the real world? And should we all stop typing in public spaces? And over the years, people have been making steady progress towards a practical keystroke inference attack. However, related work, they all assume that attacker has external information of the target. For example, label data of the target, keyboard size and layouts, finger reflections on screen, and placing sensor very close, like centimeter levels, to the target. And this is an incomplete list. And obviously, in reality, the attacker have none of these information. So we ask, can one still run a practical keystroke inference attack without such information? And in this paper, we consider a general attack, where the attacker has no external information about the target. In our threat model, the target types in English for 10 plus minutes, and the attacker has an RGB camera with unobstructed views of the user's hand. For example, like the iPad here on the right side. So basically, the attacker records the target typing and obtains a video of it. Then the attacker goes back home and analyze the video and eventually recover the text. But how? Our typing motion is very complex and very user-specific. Like in our experiment, we never found any two people type the same way. With no external information, the video is all the attacker has. Simply saying the attacker has data, but no label. What do? We learn the labels by ourselves. So our attack design follows a self-supervised learning approach, and we achieve this in 2 steps. We first automatically self-annotate some video frames, and we do so by extracting fingertip positions and analyze them across frame. And this gives us pseudo-labels for a subset of video frames. With the label, we then use them for model training, and this will give us a DNN keystroke classifier. And we use this classifier to infer every video frame and obtain a predicted character. And eventually, after inferring all the frame, we recover the whole text. Let's talk about step 1. So in step 1, we first simplify the problem from analyzing images to analyzing fingertip positions only. And we do so by applying a hand tracking tool on every video frame. Then we project the pressing fingertip locations on frame to the typing surface, and this gives us the keystroke locations. After that, we do clustering, and then we apply HMM, a hidden Markov model trained on English, to label the keystrokes. And now, because hand tracking and HMM, they are not perfect, like the tracked fingertip positions could be off, and HMM might label a keystroke P as a keystroke K. And because of that, lots of errors exist in the labels. So we develop a label filter based on consistency checks to minimize the errors. And eventually, we obtain pseudo-labels for a subset of video frames. And now, step 1 is done. And with the pseudo-labels, our step 2 is very straightforward. We use the video frames with the pseudo-labels to train a DNN keystroke classifier. And because pseudo-labels, they're not perfect, they're not ground true, so we use noise-aware training techniques to help the model learn better in this situation. And after the model is trained, we run it on every video frame. And for each frame, we obtain a predicted keystrokes. And after we infer all the frame, we recover the whole text. Okay, due to time constraint, I don't have time to talk about all the details in every component. So if you're interested, please see our paper. But I do want to point out one thing in our attack design. Our step 1 and step 2, we use 2 different data modalities. In step 1, instead of analyzing the complex video frame, we simplify the problem. We only analyze the fingertip motions to learn pseudo-labels. And in step 2, we use raw video frames free from hand tracking information to train the DNN classifier. This is because hand tracking can be noisy, and raw video frames are clean data containing rich information about the user's typing hands. And together, with the noise-aware training technique, we mitigate the impact of pseudo-labels, which we learn in step 1, and they contain noise. Okay, so that's all for our attack design. We did lots of experiments to evaluate our attack, and here are some previews. We first evaluate the attack on 16 users. They had very different typing styles, like some use their index and middle finger to type only, and some use all their 10 fingers. And each user typed about 500 words in our study. These are email sentences, and they are extracted from Enron dataset. The typing duration is roughly 10 minutes, and they all type on an iPad keyboard. We have 3 different metrics to compare our recovered text to the original one. First is CER, character error rate. Second is WER, word error rate. And for these 2 metrics, the lower the better. And finally, we have semantic similarity, which measures the amount of information we recovered. And for this one, the higher the better. And here are all the results. And the average CER is 6.8%, WER is 20.7%, and semantic similarity is 81.6%. Other than testing our attack across different users, we want to do a practical attack in the real world. So my colleague and I, we went to one of the buildings on campus, and I sat down in the courtyard and typed on an iPad keyboard. And my colleague recorded my typing inside the building, 2nd floor, through glass, with glare, and long distance, roughly 12 meters away. My colleague was using an iPhone plus a telephoto lens that we bought from Amazon to capture a video. And here is a video of the experiment. And even in this environment, the attacker successfully recovered 87.2% of the content, which is truly alarming. Then we went one step further. In this experiment, we use a green screen technique to remove the keyboard completely from the video. So the only information used by the attack is the user's fingers. And again, our attack is successful. We found no performance degradation, just like the case when the keyboard is visible. Okay, so by now, I hope that we have convinced you that a practical keystroke inference attack are very feasible in the real world, and we must be careful. So what if we still want to work and type in public spaces? We recommend using a physical shoe to prevent others from observing your fingers, typing fingers. Thank you. Now I'm ready to take questions.